Our next speaker is Nicolas Lehner from Notre Dame, and he will be talking about KODIAQ-Z, metallicity of the IGM galaxy interface at Z of 2 to 4.
Okay. Can you see my slide? Yeah.
Looks good.
All right. Thank you. And thank you for the organizer to give me the opportunity to present an update on KODIAQ. For those who don't know, the KODIAQ is Keck, the Keck database of ionized absorbers toward QUASARS. It's a program that has been driven by both CGM science, but also releasing high-level data products in the KOA. This is a core team, and I will highlight in particular John O'Meara, Chief Scientist at Keck, who has been the heavy lifter to actually reduce all the arrays and ESI data that we've been using to do science. So what is the science of KODIAQ? One of the main questions that we have is, how is the circumgalactic medium, the gas that is at the interface between the intergalactic medium and galaxy have evolved over cosmic time? Our methodology has been to search for hundreds of quasars absorbers, but not just blindly quasar absorber. We want them to have H1 current density in the range between about 10 to 15 to about 19.5 per square centimeter. And that's basically how we define the IGM galaxy interface. And that's based both on observation of galaxy and absorbers, as well as simulation that both show that in this H1 current density range, they are closely associated with galaxies. And that applies to both low and high redshift. Because we want to understand how the gas evolved over cosmic time, we actually have to study both from the space using HST cost for redshift less than 1, and from the ground using Keck arrays and also ESIM, that's the KODIAQ program. If there is one point that you should take away from my talk, is that archives are important and are critical to do science, this type of science, because without this high quality of spectra in the Keck archive, KODIAQ would never have seen the light. So this is just to show in parallel. I'm not going to go really through the slide, but basically the point that I want you to take away is that just a few years ago, we were working basically with only a handful or 2 handful of absorbers, and now we're working in the H1 condensity range with several hundreds of strong H1 selected absorbers, and that apply both at low and high redshift. Before I jump into the metallicity, I can't talk about KODIAQ without talking about Oxygen-6. That was the primary science driver of the original KODIAQ program. And that's also allowed me to show you a beautiful Keck array spectrum here. This is the normalized flux as a function of velocity in the west frame, redshift west frame of a Lyman limit system, and that stack of velocity profile going from the top to bottom, from low ion to the high ion like Oxygen-6. And Oxygen-6 has been this key ion that has been neglected for a while because it's deep in the Lyman alpha forest. But as we've been showing by looking out, we actually can find cases like this one where there is actually no contamination from the Lyman alpha forest. And the point that here I want you to take away, if you compare all these ions, is that Oxygen-6 doesn't compare at all with the other ions. It's very broad, it's actually very strong, and that's a common feature that we've been seeing actually in the high redshift CGM when we select the absorber based on the H1 content. This is a plot showing the total Oxygen-6 current density as a function of the total Oxygen-6 velocity width. And here, this is the CGM at redshift less than 1, and you can see that this redshift greater than 2, we find very strong Oxygen-6 absorbers that are not found in the CGM in the low redshift. And we argue that this is principally because there are many more starburst galaxies occurring at high redshift, producing this very strong and very broad Oxygen-6 absorption. Changing gear here, and going on the current survey, that's KODIAQ-Z, which is the goal is to map the metallicity of a gas at this interface between galaxy and the IGM. On the left here, what I show is a cosmological simulation, and this is what we would love to do with observation, but we're not quite there yet. However, what we can do with absorption line, and also what we can do from the simulation is we can show the plot of the metallicity as a function of H1 condensity. And for a very long time, we were focusing mostly on H1 absorber greater than 10 to 19 or so, or below 10 to 15. And what we've been filling up is that region between the neutral gas and the very highly ionized gas seen in the intergalactic medium. And this is the result from CCC. This is the low redshift survey. And if I did show you this plot just 5 years ago, there will be only about 30 data points in the blue. And if I did show it 10 years ago, only 5. So we have now 300 absorbers here. So, and this is over 6 decades of H1 condensity. And you can see we have a much clearer picture of the metallicity distribution of H1 condensity, showing a very strong change as a function of H1 condensity. But thanks to the Keck database and KODIAQ, we're also now working on filling up what's happening at high redshift. And the red data points is from a paper that I published a few years ago in 2016. And the green data point is the ongoing survey that we do with KODIAQ using the ARES and soon the ESI data. And so right now we have about 60 data points here between about 14.9 and 19. I should also mention that the gray data points here are from the LGLS survey, and each of these data points have several tens of Lyman systems. But this survey was mostly focusing on higher H1 condensities. And you can see, I don't have time really to explain all the richness that we get from this plot, but you can see also that there are some observers comparing from high redshift to low redshift, so that have not evolved over cosmic time. We find very low metallicity gas and very similar metallicity at both high and low redshift. You can also see that there is a lack. There seems to be a lack of very metal-enriched gas in the low H1 condensity. So with KODIAQ-Z, we hope in the next few months that we will increase the sample by a factor 5 to have a very metallicity sample. And just to wrap up, I want to advertise the latest KODIAQ data release. This is the number 3. And this is a release of 727 quasars at redshift 0.1 to 6.4 that were observed with ESI. And John has just submitted the paper to AJ. The link is not live yet, but it should come very soon at the KOA. And of course, without the PI, who actually obtained all this ESI data, would not have the KODIAQ DR3, so we thank them. And in summary, so KODIAQ DR3 is coming live soon. KODIAQ-Z, I hope in the next meeting in a year or so, I will be able to show you much more finalized results for the metallicity at high redshift and how it evolves with over cosmic time. And again, a big thank you to all the Keck PI as well as the KOA and also all the organizers for a great conference so far. Thank you.
Thank you, Nicolas. Questions for Nicolas? Again, we can do Slack or on the Zoom Q&A. All open while we're waiting for people to type. For KODIAQ, you've done DR1 and 2, which were mostly high-res, if I recall, and now DR3, which is ESI.
Right.
Is this going to keep going? Are there going to be other instruments in the future years?
We're looking at other instruments, in particular LRES, to look to the galaxies, but this is very early work. So I will probably say more in a year. But yeah, we're looking at other data set in the KO, yes.
There's another question. Will there be continuous data release as new ESI high-res observations come in?
This is something that we will discuss with John. I think it's going to depend also a bit of how the KO is going to evolve by, the type of data that are going to be released in the KO. But it's possible before the end of the KODIAQ program that, yeah, we will release more data, yes.
Great, thank you very much.
Thank you.